So this is a very interesting lecture on the applications of linear systems. Here we're going to look at basically two main applications. The first of these is on polynomial interpolation. So polynomial interpolation, basically what we're trying to talk about is if we look at the situation where we have any experiment or anybody who is trying to understand the relationship between any variables, usually you will find that they will have an x and y axis, a horizontal and a vertical axis, and they'll have a variable x and a variable y. And experimentally they will be recording values, and then they will try to do what we call a scatter plot, which is essentially to try to plot the points which have been experimentally observed, and then try to see if there is a mathematical underlying pattern that describes those points. And if that does exist, we say there is a correlation between the two variables, and if it doesn't exist, we say there is no correlation. Now, we're not going to be looking at, in fact, the concept of correlation coefficients, but which is also related to the same idea. But here we're going to look at the mathematical part, the mathematical model that can possibly fit this data. Specifically, we're going to look at polynomials that can actually be considered that fit the data best. So in order to do this, we start with the fact that any nth order polynomial, basically, so let me do that again. So any nth order polynomial y, okay, is in fact looks like this. So had we if we have n data points available to us, a combination of n data points, then what we can do is basically all these n data points would satisfy, if this equation were to fit those data points, then all those n data points would satisfy this particular polynomial equation. So what you essentially do is you substitute all in the values into this equation, and it gives you a bunch of equations. In fact, let me show you what I mean. Suppose that let's identify the points as being x1, x2, and y1, y2. So for instance, suppose you have the pairs are described as x1, y1, x2, y2, and so on up to xn, yn. So these would be the pair of data points, okay, that we have that represent this graph, for instance, the scatter plot. So now what we do is we will start substituting these values in. So as we substitute the first pair of values, it gives us that y1 must be, because if it's x1, y1 satisfies the equation, then we should get a1 x1 plus a2 x1 squared, and now you have to realize, please, that the x1s that you see here, okay, these x1s are all known values. Okay, don't confuse them with unknowns. These are known values. So the only thing that we don't know in this equation are the a's, in fact, right? So the a's are unknown. Now in the same way, if we continue, and the second equation then is going to be x2 this time. So we get this equation, right? And in this manner, we have all these equations up to the nth point, which is in fact, okay. So that's how we get these equations. So these equations then, now if you look at this is a linear system of equations, because remember the powers are already, the x1, x2, xn are known values. So when we substitute them in, I mean, these would be numbers that we would have. When we substitute these numbers in, all we would have are in the unknowns that you'll see in this equation, or in these equations, would be the a's. So essentially what happens is, if I were to write this as a system of equations, then what happens, I mean, in an augmented matrix, for instance, this is what results. So basically, if I look at this as follows, what is the coefficient of A0? It's 1. What is the coefficient of A1 is x1. The coefficient of A2 is x1 squared. And so on up to x1 n minus 1. Right? So that's what I would get. And the right-hand side, okay, would be y1. In the same way, the coefficient of, in the second equation, the coefficient of A0 is again 1. And then you have x2, and then you have x2 squared. And you have x2 n minus 1 and y2. Sorry. So this continues. These are all 1s, in fact. And these end up being up to xn. This is going to be xn squared all the way up to xn to the n minus 1 and yn. So we end up with this system of equations, in fact. Now, if you look at this, this is the connection that we're trying to make. It's an application of linear systems. Here's our linear system. We will use Gaussian elimination, Gauss-Jordan elimination, inverse, whatever method you feel appropriate that is the most efficient to solve this, and essentially solve the system of equations. Once you have solved the system of equations, what you have found, in fact, are all the coefficients. And that's in fact, these values of A0, A1, A2, AN. So once you plug them in here, you'll get the polynomial that best fits the data that you are trying to fit. Let's look at a quick example. So the example that I'm using here is again taken from Howard Anton's Elementary Linear Algebra, Anton and Rores. So if I were to just to relate this back to what we have done, the methodology that I've just shown you here with the x1 and y1 data points. So here, this is what I meant. This is x1 here, and this then would be y1. Okay, so these are your pair of values. These are the x and y values. So now you see what I'm saying. If I were to take one of these for the sake of argument, so this is your x1. This is this is x1. This is x2. This is x3. This is x4. So if I were to substitute it into these equations here, or into this matrix, then what I would end up with is this system here. Now, so here, what you'll notice is one important thing that we need to understand is how many data points do we have. So we have, you will notice that we have, in fact, 1, 2, 3, 4. So we have 4 data points. That means we are looking at an n equals 4 situation. So n is equal to 4. Now, first of all, you have to keep in mind, we are going to be fitting a cubic polynomial to this, because what you're saying is that we're looking at fitting this polynomial. So it's going to be a0 plus a1x plus a2x squared plus a3x cubed. So we will be fitting this polynomial to this set of data that we have. So let's just quickly look at how this works for one of the data points, for instance, just quickly. So if I were to substitute in the 1, 3, that means that 3 would be equal to a0 plus a1 plus a2 plus a3. The second point would be minus 2 is equal to a0 plus 2a1 plus 4a2 plus 8a3. So in the same way, I can continue on, and let's do that because it's just a very small, it's a smallish system, so we can in fact do that quite easily. So here, if I continue to the next one, it's going to be minus 5 is in fact equal to a0 plus 3a1 plus 9a2 plus 27a3. Okay, and the last one, of course, is going to be 0 is equal to a0 plus 4a1 plus 16a2 plus 64a3. So now, of course, that's not what you practically have to do, because we've already shown here, if you'll notice, this is, and in fact, the system that's always going to be there. So I was just trying to demonstrate how the equations come out, but you could directly go to the, in fact, the system, and the system from this is going to be, of course, 1, 1, 1, 1, 4 rows, okay, because there are we're going for a fourth order polynomial, so you'll get that, and then you'll have, of course, the x1 value, which is 1, x2 is 2, x3 and 4, and then this and then the it's the square of these numbers, so it's 1, 4, 9, 16, and then the next column is 1, 8, 27, and 64, and then we have the right hand side, and the right hand side are 3 in the order we've taken, -2, -5, and 0. So see, you can directly write that system down. Now, of course, the next thing you do, of course, is solve the system of equations, and you can see that here one would be needing to use Gaussian elimination or Gauss-Jordan, whichever one is possible, or which one you prefer to use. And if we do that, in fact, I'm just going to not go through that process. We end up with this matrix. Again, I'm just using this the textbook because the example is already here. Now, this implies, of course, that our polynomial, okay, is in fact our polynomial y is equal to 4 plus 3x minus 5x squared plus x cubed. So this cubic polynomial should be a reasonable fit to the data that we had. And of course, the data points themselves fit perfectly if you were to substitute them into Zika, because that is, in theory, that's what we have in fact done. That's how we've developed this. So this is a very nice little application of linear systems of equations. I'm not going to really talk about applications of polynomial interpolation because that is not part of what we used to do, but there are so many applications of it that in fact the list is almost so the next example, the next application we will look at, again taken from Anton, is a collection of some very good applications, in fact, and covers, as I said, this material quite well, is network analysis using linear systems. Basically, a network can be considered as a bunch of branches that represent, there's some flow through these branches, and there are junctions or nodes, which we call nodes, where these different branches meet or sprout from, and basically, so if I were to draw this quickly, we would be saying that suppose there are a bunch of branches, like for instance here we call this a node, okay, or a junction, and there is this is one branch, this is another branch, okay, there's another node, then there is another branch, here's a node, here's another branch, and there could be more than one branch, and so on. So, and then there's some flow through these, and of course, in most networks, we are looking at some form of a closed loop sort of a system. It could be like this, for instance, okay, where there is some flow. Sorry, from that node to this node. In this way, maybe this way, maybe this way. These indicate that there is some flow from these nodal points or junctions. Now, these could be anything. I mean, these could be traffic systems, this could be electrical circuits, they could be pipes through which water is flowing, through which oil is flowing, any other fluid is flowing. So, what we're looking at is that that fluid that goes in, or something that flows into the node, and then also distributes out of the node. Now, for the purpose of simplicity, we will be assuming a conservation of flow here, in the sense that through the nodes, that means that whatever goes into the node must also leave the node. And this is an important assumption to make to help model these situations. So let me quickly show you an example. So what I've drawn here isn't all that great. So let me just quickly do that. Let's get rid of this, and let's draw this system. So here's a nodal system that we will look at. So there is, for instance, 60 per rate. So these are rate of flows. So you know that something is flowing in at a particular rate, like 60 units per minute or hour or whatever it is. So if it's cars, for instance, it could be at a traffic light, 60 cars per hour, or and so on and so forth, for instance. And here, for instance, we have this, and then the, sorry, my writing is crap. My drawing is worse. Okay, so let's look at this system, for instance. So you have some rate here, 60, suppose 60 cars per minute or hour, sorry, not per minute, 60 cars per hour flowing into this, you know, for instance, the traffic, or it could be water that's flowing into this junction in a pipe. It could be electricity in, say, for instance, amps, and water, it could be 60 liters per hour or per minute or whatever is appropriate, flows into the junction, and then it flows out at about 15 liters per minute or per hour in the same unit, of course, measure, goes into this junction, and then flows out at 55. Now, we don't know what's going on here, so we'd like to find out what's going on here. We don't know what's going on, and we don't know the direction of flow, and the same here. We also don't know the direction of flow in this case. Here we do know, for instance, in the top, we're given that it's coming in at 30 units per time measure, and here it's flowing out at 35. Now what we can do is we will assume the positive direct, I mean, we can name these nodes, for instance. Let's say this is A and B, C, and D, and let's say that this is node, we'll call this, I mean, this flow rate x3, this one is x1, and we'll say it's in this direction, being positive, and this is x2. Now we can actually set up some equations. So what is basically the easiest way to do this is to look at, for instance, if you look at so if you look at the 30, for instance, that's flowing into here, this 30 is flowing into here, and it's distributing into these two equally. Let's assume, well, we don't know equally, I mean, sorry, pardon me, say that again. So this 30 flows into this junction, and x1, x2 flow out. So that means that the sum of x1, because we said there's conservation, that's the reason we made that assumption. It's because that'll give us this equation, x1 plus x2 equals 30. Now if we look at the next node, for instance, this node here, so we have this 15 is flowing in, this x1 is flowing in, so x1 plus 15 gives you 55. So you have x1 plus 15 is 55. This immediately tells you, well, let's write them all down. The next node here, this one, is clearly the 60, the x3 plus 15 must be 60. So let's write that down as well. So x3 plus 15 is 60. And the final one is, which you can see, node B, is that x2 plus x3 equals, in fact, 35. So we have if you see here, we have a set of equations. Now, this is a very easy system. Clearly, we can identify the value of x1 very quickly from this one, from this equation here. Okay, this tells us that x1 is clearly 40. Okay, and this one here tells us that x3 is in fact 45. So we already know x1 and x3. We can just substitute the x1 40 into this equation here, and that tells us that x2 in fact is minus 10. Okay, so minus 10. Now, just to interpret, if it says minus 10, it would mean that the direction we've chosen for x2 here, you will see it's in fact not going to go in that direction. In fact, it's going to go in that direction. So the x2 is going to be going in that direction, in the opposite direction to what we have drawn here. So it'll be like this. So it will be like this. So that will be the flow for x2. So, and you can see that here what's happening is, if you look at x3, so let me just now put these numbers here, and actually everything makes a lot of sense. So here you'll see 45, in fact, x3 is 45. So you have 45, the 60 is well split into 15 and 45. That 45 flows in here, 35 of it goes out over this node here, and the remaining x2, which is 10, goes here, minus 10, so that you see this adds up to 35. So if you look at it, it's very logical, makes a lot of sense, in fact, and it's very easy to understand. But the important thing for you to grasp is that this is a network that has been solved using, or can be solved using, linear systems of equations. The example I've looked at is a rather straightforward one, and you can apply this to, in fact, traffic systems, where you would be looking at, you've noticed traffic lights. I'm sure that traffic lights have different opening and closing times, and you must have thought, why, when you're standing on this traffic light, why the other side, opens for so long and yours opens for such a short time, and you're really not very happy to see that, and maybe wished you were on the other side. But the fact is that there is a reason why there is a difference in the timing. It is to keep the flow of traffic as smooth as possible. And obviously if it opens less of a period of time for the lane you're in, it's obviously because there is less flow of traffic from there. But somebody has to do this analysis and then actually come up with a reasonable opening time to keep the flow without any backing up of traffic on that particular lane, because every lane will affect, yourself that a traffic system itself is it's in fact a very complex network, and it does have all these junctions and nodes, and therefore not only accidents, but even if there were, in the absence of accidents, any junctions where you could have a possible bottleneck of traffic, and the flow is too slow to accommodate the flow, it could back up into an effect a joining junction or an earlier junction. So network analysis is a very powerful tool, a very powerful and very usable concept, and it's not just applicable to traffic systems, it is applicable to economies, even where money can be thought of flowing in and flowing out, or being distributed from different banks, and so on and so forth. I would advise you to have a look at there's a design of traffic patterns example in the textbook, Anton and Rory's Linear Algebra. I would advise you to have a look at it. It's a bit more complicated, but it also gives you a very good idea about how these networks work. We'll stop here with the applications.